This Spark job is slow, really slow. It takes around 41 minutes and 32 seconds to finish. And today, my goal is to make it much faster without changing the final business output. But I'm not going to optimize it like a beginner. I'm not going to randomly increase the memory. And I'm not going to blindly change Spark configs. And I'm not going to copy tuning tips from the internet and hope something works. I'm going to debug it like a senior data engineer. First measure, then find the bottleneck, then fix one problem at a time. By the end of this video, we will complete the before and after results, and I will give you a Spark optimization checklist you can use on your own jobs. Hello everyone, welcome to Big Data Factory. I am Pranit and I have over 40 years of experience working as a data engineer. And if this is your first time visiting this channel, don't forget to subscribe for more content on big data and real world insights. Here is the job. We have orders data, customers data, products data, and clickstream data. The goal is to create a revenue attribution table. Basically, we want to answer which products are generating revenue, which countries are buying, which marketing campaigns are driving orders, and which customer segments are performing best. This is a realistic Spark job because it includes large reads, filters, joins, aggregations, and writes. But I intentionally made this job slow. It has common problems I see in beginner Spark code. It reads too much data, it keeps unnecessary columns, it has expensive joins, it has skew, it uses a slow Python UDF, and it writes too many files. For this test, the orders table has around 60 million rows. The clickstream table has around 120 million rows. The customer table has around 5 million rows. And the product table has around 100,000 rows. So this is not a tiny toy example. It is still manageable, but big enough for Spark problems to actually show up. Now let's optimize it. Before changing anything, we need a baseline. The original job runtime is 41 minutes and 32 seconds. The biggest stage takes 24 minutes and 9 seconds. The shuffle read is 186 GB. The job produces 3842 output files. And in the Spark UI, we can see three major problems. First, there is a lot of shuffle. Second, there is around 58 GB of shuffle spoil. And third, one task takes 21 minutes and 44 seconds, while many other tasks finish in less than a minute. That usually means skew. This baseline matters because optimization without measurement is just guessing. If we don't know where the time is wrong, we might optimize the wrong thing. So the first senior lesson is, do not start with configs, start with evidence. Now let's inspect the job. In the Spark UI, I am looking for the slowest stage. Not the line of code I personally dislike, not the transformation that looks completed, the actual slowest stage. This is important because Spark is lazy. The code you write and the physical work Spark does are not always the same thing. In the UI, I'm checking which stage took the longest. Was there a large shuffle? Did any task spill to disk? Or some tasks much slower than others? Are there too many tiny tasks? Is one join causing most of the delay? When I look at this join, the biggest problem appears around the join and aggregation stage. The slowest stage is taking 24 minutes, the shuffle rate is 186 GB, and the max task time is way higher than the median task time. This tells me we probably have too much data moving across the cluster, and this data is not evenly distributed. So let's fix the simplest thing first, read less data. Fix number one, read less data. The original job reads the entire orders dataset, but the business only needs the last 90 days of data for this revenue attribution table. That means we are wasting time reading data we will throw away later. So I push the filter earlier instead of reading everything and filtering later. I filter as early as possible. This allows Spark to skip unnecessary partitions if the data is partitioned properly. This is one of the most powerful optimization ideas. The fastest data is the data you never read. After this change, the runtime becomes 28 minutes and 14 seconds. So just by reading less data, we cut the runtime from 41 minutes 32 seconds to 28 minutes 14 seconds. This is already a big improvement, but we are not done because the job is still carrying too much unnecessary data. Fix number two, select only the columns we need. The original job reads many columns from orders, customers, products, and clickstream, but the final output only needs a subset. Keeping unnecessary columns increases memory usage, network transfer, and shuffle cost. So I select only the required columns early. For example, from orders, we only need order ID, customer ID, product ID, order date, quantity, revenue, country. From products, we need product ID, category, brand. From customers, we need customer ID, segment, and country. This looks simple, but simple optimizations often matter. After this change, runtime becomes 22 minutes and 7 seconds. So now we went from 41 minutes and 32 seconds to 22 minutes and 7 seconds. At this point, we have almost cut the job in half. So far, we have reduced how much data Spark reads and how much data Spark carries. Now let's deal with joins. Fix number 3, improve the join strategy. This job joins a large orders table with smaller dimensions table like products and customers. If a table is small enough, we can use a broadcast join. That means Spark sends the small table to each executor instead of shuffling the large table unnecessarily. But this is where you need judgment. Broadcast joins are useful when the table is actually small enough. If you broadcast a table that is too large, you can create memory problems. So I check the size of the dimension table first. The products table is only around 100,000 rows. So this is a good candidate for broadcast. The customers table is around 5 million rows. So I am more careful with that one. I broadcast the products table, but I do not blindly broadcast everything. After applying the better join strategy, runtime becomes 13 minutes and 48 seconds. Now this is a serious improvement. We started at 41 minutes and 32 seconds. Now we are at 13 minutes and 48 seconds. But there is still one big issue. One task is much slower than the others. That usually means skew. Fix number 4, handle data skew. Data skew means data is not evenly distributed. For example, maybe most order comes from one country, or one customer ID appears millions of times, or one product category dominates the dataset. When that happens, most tasks finish quickly, but one or two tasks take forever. The whole job waits for the slowest task. This is why skew is so painful. In this job, I can see that one key has more records than the others. The country value US has much larger number of rows than any other countries. So when Spark groups and joins by country, one partition becomes much heavier than the others. Before fixing skew, the maximum task time was around 21 minutes and 44 seconds. Most of the tasks were finishing much faster. This is a classic skew pattern. To handle this, I use salting for the skewed key. The idea is simple. Instead of sending all records for one huge key into one partition, we split that hot key across multiple smaller buckets. Then we aggregate safely after that. After handling skew, runtime becomes 8 minutes and 26 seconds. This is the point where job starts feeling completely different. We went from 41 minutes to 8 minutes. But there is one more classic beginner problem, Python UDFs. Fix number 5, remove the slow Python UDF. The original job uses a Python UDF to classify customers into segments. It works, but it is slower than using built-in Spark functions. Why? Because Spark's built-in functions are optimized. They can be planned and executed more efficiently. Python UDFs often force Spark to move data between the JVM and Python processes, which can become more expensive. So I replace the UDF with built-in Spark SQL functions. Instead of custom Python function for customer segment logic, I use when, otherwise, case, or SQL expressions. The business logic stays the same. The output stays the same, but Spark can execute it more efficiently. After replacing the UDF, the runtime becomes 5 minutes and 41 seconds. This is a great example of senior thinking. The goal is not to write clever Python. The goal is to use Spark the way Spark is optimized to run. Now the job is fast, but there is still one problem that can hurt future jobs: the output files. Fix number 6, fix the output files. The original job writes too many small files. It produces 3,842 output files. This is a common problem in data lakes. Too many small files make future reads slower. They also make storage and metadata management worse. But the opposite problem is also bad. If you write too few huge files, you may reduce parallelism. So the goal is to write a reasonable number of files based on the data size and downstream usage. I adjust the partitioning before writing, not randomly, based on the output size and access pattern. After the fix, the job writes 128 output files. instead of 3842 output files. The runtime also improves slightly. After fixing the output file problem, the final runtime becomes 4 minutes and 8 seconds. This helps not only this job, but also future jobs that read this output. That is another senior lesson. Optimization is not only about today's job, it is also about the jobs that comes after it. Now let's compare before and after. Runtime 41 minutes and 32 seconds. Slowest stage 24 minutes and 9 seconds. Shuffle read 186 GB. Shuffle spill 58 GB. Output files 3842 files. Max task time 21 minutes and 44 seconds. After, runtime becomes 4 minutes and 18 seconds. Slowest stage 1 minute and 52 seconds. Shuffle read 31 GB. Shuffle spill 1.2 GB. Output files 128 files. Max task time 49 seconds. This is around 9 times improvement. But the bigger win is not just the runtime. The job is now easier to reason about. It reads less data. It carries fewer columns. It uses better join strategies. It handles skew. It avoids slow UDFs. And it writes cleaner output. This is what real optimization looks like. Here is the difference between beginner and senior Spark optimization. A beginner sees a slow Spark job and says, maybe I need more memory. A senior asks, what data am I reading? Am I filtering early? Am I selecting only required columns? Where is the shuffle? Is there skew? What joint strategy is Spark using? Are there spills? Am I using UDFs unnecessarily? How many files am I writing? Where does the Spark UI actually show? This mindset matters more than memorizing random tuning tips. So here is the Spark optimization checklist. First, measure the baseline. Second, inspect the Spark UI. Third, read less data. Fourth, select fewer columns. Fifth, check joint strategies. Sixth, look for skew. 7. Avoid Python UDFs when built-in Spark SQL functions are available. 8th, manage output file sizes. 9th, compare results after each change. And 10th, do not optimize blindly. The main lesson is simple. A slow Spark job is not solved by guessing. It is solved by evidence. Measure first, find the bottleneck, fix one thing at a time, and always make sure the business output stays the same. Here we started with a job that took 41 minutes and 32 seconds. We ended with a job that took 4 minutes and 8 seconds. Same business output, much better execution. This is how you optimize Spark like a senior data engineer. Comment optimization and let me know in the comment section which optimization you have used in your production pipeline. If this helped, drop a like and subscribe to Big Data Factory. This is all for today. I will see you in the next video. Till then, keep learning and keep building. Bye bye.